Hi guys, I'm Nidhi. I'm going to be covering two oxidation reactions that you learned for the final exam, and I'm also going to be going over some tips and tricks that I thought would be good to point out before you take the final exam. So let's get started. So the Swern oxidation and Des-Martin oxidation are two alternatives to using chromic acid, or not just chromic acid, but chromium as a molecule in oxidations of alcohols. And both of them work the same way as using PCC or Jones reagent or any other chromium containing compound, because we go from an alcohol to a carbonyl containing compound. So this is just an alternate method, and it's actually more preferred because they're using chromium is a little bit unfavorable in some conditions. So these are some more modern oxidative mechanisms. One thing I did want to point out is we don't need to know the mechanism. You guys don't need to know exactly what's happening in terms of like arrows and like intermediates, but I did include pictures here from the Brown textbook in case you wanted to see, and I made some points that I thought were relevant in case you were asked about this reaction, or if you just see something about this reaction, and this will hopefully give you the hint that this is what's happening. So one point, we'll start with Swern oxidation. One point that I wanted to make is pay attention to all the reagents. And I've also drawn them out over here. If you see these reagents next to an alcohol like this, there's a good chance it's going to be a Swern oxidation. That's actually the only reaction that can occur under these specific conditions. Just don't be too intimidated, because if you see, it's literally going to give you the same product as a Jones reagent or a PCC would give you, a reaction using those two reactants. The only difference is we have this molecule, this COCl, and then two of those. We have dimethyl sulfoxide, which is a common SN2 solvent, if you remember. And we have this intermediate that I just showed in the screenshot from the textbook. The only reason I included that is because I included -78 degrees Celsius in our reaction conditions, because you may or may not need to know this, but this intermediate can only be made at this temperature. And so I thought I'd just include that over here. And then this is the second step where we actually incorporate the alcohol and then this deprotonating agent, which is just NET3. So NET3 is a strong base because nitrogen containing compounds in general are good nucleophiles, are good bases. And then having these ethyl groups, which is what ET stands for, make them even more basic. So we're going to use that to deprotonate a hydrogen that's attached to this carbon that bears the OH. And that is exactly why we don't see this reaction occurring, nor do we see the Des-Martin oxidation occurring with tertiary alcohols. Because if you think about it, a tertiary alcohol doesn't have space for a hydrogen to be attached at that position. It would look like this. So there's absolutely no place for us to attach a hydrogen, therefore there can be no deprotonation, and this deprotonation is what makes this an oxidation. So like I said, you don't need to know what happens in that deprotonation, but I just thought I'd point out that this reagent is what does the deprotonation, and that the reasoning behind not using tertiary alcohols for Swern oxidation and for Des-Martin oxidation is that there is no hydrogen to deprotonate if we use tertiary alcohols. However, using secondary alcohols, primary alcohols, that's exactly what we're going to use for these. And you'll get two different products depending on the kind that you use. So in the Swern oxidation one, I wanted to look at a primary alcohol as our example. If you see here in the screenshot, they used a secondary alcohol, and we ended up with a ketone with these two R groups that were in the initial alcohol becoming the two R groups in the ketone. For primary alcohol, we're going to end up with an aldehyde. So it's going to look like this. And because it's an aldehyde, we're going to have an H over there. And I did make sure to count my carbons to make sure I'm not forgetting anything or adding anything extra. So that would be the product of this reaction, the Swern oxidation. Not too different than what you'd expect from PCC or something else. So the only thing you would expect is if this was a Jones reaction, then this OH group would be converted to carboxylic acid, not just an aldehyde. So that's another difference between this oxidation and other alcohol oxidations. So that's Swern oxidation. Let me just do an example for Des-Martin oxidation. Once again, I included the screenshot from the textbook. And one new thing about this reaction that is different from the Swern oxidation is this molecule DMP, which stands for Des-Martin periiodinane, or I think that's what it's called. It's in the textbook, but all you really need to know about that, and all you probably need to recognize, is this molecule if you see it on your exam, or maybe Dr. Lopez will abbreviate it as DMP. And this is a hypervalent compound not necessarily this is different than this, but this molecule DNP, this is the DNP molecule, is a hypervalent compound. It exceeds the octet rule. So if you see this compound and you see it in conjunction with an alcohol, especially primary, secondary alcohol, then you know you're undergoing a Des-Martin oxidation. Once again, you don't need to know the mechanism. I just drew it out over here or included a screenshot in case you were interested. But all that you really need to remember is that we're just going to convert the alcohol to a carbonyl compound. We're going to replace that OH with the double bonded CO. Right in the same position it was here, so the second carbon, and that would be the product of this reaction. So in conclusion, these oxidations are not too different than other oxidations of alcohols we've seen. Just be familiar with the reasoning why we might use this, which is basically so that we can avoid using chromium in our other oxidations, just because that's a less favorable reactant. Now I'm going to go over some tips and some important details for you guys to remember. So if you're watching this in advance, maybe save this part till right before your exam, or watching in advance, just make sure you remember these when you take your final exam. These are some common mistakes. The reason I've come up with these is because we've seen some common redundant mistakes that a lot of students have been making in exams and in practice. And so we just wanted to clarify some things. So the first thing that I wanted to point out is to remember to show your Stereochem at all chiral sp3 hybridized carbons. And the reason for that is sp3 hybridized carbons have a tetrahedral geometry, remember, with the 109.5 bond angles. So that means there's some three-dimensional character to that molecule when it has tetrahedral geometry. So we want to make sure to show that, especially with chiral molecules. So I drew this molecule out because if you see, this is not a chiral molecule. We have two similar groups here. These two methyl groups are similar. So this one you would be fine with just drawing like this. Obviously, we draw it like this by convention because we don't really draw hydrogens in our line angle formulas. But let's just say this was another molecule as well. It was ethyl. You would still write it like this. You wouldn't need to include the Stereochem, because once again, these two ethyl groups are identical, these two methyl groups are identical, so it's not a chiral compound. So you can end up leaving it like this, and that's completely fine. Now this one, we've seen people drawing their molecules like this frequently, where we have a chiral molecule, we have 4 unique groups attached to this central carbon, and the issue with this is that we're not showing which face this OH is on. We're not showing which face this bromine is on. So we need to show chirality. We need to show Stereochem here. So this is just a way to show that Stereochem. Depending on which reaction you're doing, obviously, you have to pay attention to what that correct Stereochem would be. But we have done a lot of reactions this semester where the products that we get through the mechanisms end up with chiral molecules. And in those chiral molecules, it is essential to show that tetrahedral geometry and show that Stereochem to get all the points for those questions. So that's one thing to remember. Another thing is just to remember to count your carbons when you're doing your reactions on exams and in practice. I know that with a time crunch and with the stress, it can be easy to forget to include a carbon here or there, like especially when you're undergoing a reaction. Like the reaction that I want to put this molecule through is just a simple reduction. We're going to convert this to an alkene, and a lot of mistakes happen, especially with alkynes, because I think they're just more prone to be a little bit more confusing. So with alkynes, especially, no matter what reaction I'm doing, I always like to number them. So I'm going to number 1, 2, 3, 4, 5. So this is a 5-carbon compound. And whenever I number these in terms of counting carbons, I don't really number them in terms of naming rules. I only number them in terms of making sure I have the right number of carbons. So that's why I numbered 1 through 5 arbitrarily from that side of the molecule to the other side. So now I know that my molecule is going to have 5 carbons in the end. Let me redraw that. So that's my 5-carbon backbone. We're going to have a bromine still on a wedge here. And we're going to have the alkene between carbons 1 and 2 over here, or over here, I should say. So here it was easy for me to keep track of the fact that this carbon is this carbon over here, or that this carbon, the one that I just circled in blue, is this carbon over here. But a lot of times people might leave those out. Some people might add an extra carbon where there wasn't one to begin with. So it's always important to remember to number them, because it really only takes another like 1 or 2 seconds just to go through and number it. And then that way you can keep track of your answer as you're working through it. And when you check your work, you can make sure that you counted your carbons correctly and that you have the correct number of carbons in the final product. One more thing to do is to circle your substituents so you don't forget to draw them as you do your reactions. So obviously when some molecules get more complicated, we might have tert butyl groups, we might have other substituents. If the reaction isn't necessarily occurring at that substituent, it's really easy to forget to include that. So just circle them. So if you have like a molecule like this, where we have a benzene ring, and the molecule is just undergoing a basic radical bromination, right? With all of these reagents. It might be easy to forget to include that bromine, or not that bromine, that benzene ring, because the reaction isn't really involving the benzene ring, but circling it can help you, because when you're looking back at your work, you'll remember that, oh, I forgot to draw that, or you might not have forgotten, but it might be there. It might help you anyways. So that's just one thing to remember. Another thing to remember, I should say. Then the next tip I have is, or not the next tip, the next point I wanted to make is that alkynes have a linear geometry. So they're 180 degrees. And I actually incorrectly said that these were hybridized like that. So alkynes have a linear geometry, they're 180 degrees, and they're CSP hybridized. So those carbons are SP hybridized. So drawing them in this way with a kink right over there at the end of that alkyne is actually incorrect, because the correct way to draw that would be to give it space. See how this is like linear, it's 180 degrees. That's exactly the correct way to draw the alkynes. And if you don't draw them this way on the exams, you'll end up getting points off, because this is just testing your basic knowledge of linear geometries of alkynes. So just remember, whenever you have alkynes, do not draw them like this. This is completely wrong, but draw them like this instead. One more thing is, well, not one more thing, I have more stuff, but ranking acidity and basicity. This can be challenging to a lot of people, but this is a chart that I like to go through. And I always start here at charge. I always first look at charge, and that's like the most important thing that I look at to begin with. And then as I go down this list, it becomes less and less important. So I use the criteria above on this SERI chart, which is what we call it. I use like the charge, size, electronegativity to figure out the acidity and basicity, and I move down this chart. So basically charge, one thing I wanted to mention with that is any charged compound is going to be more acidic / more basic than the neutral compound. So if we have hydronium, H3O plus compared to H2O, because H3O plus has that plus charge, it has a charge, it's going to be more acidic. Also, if we have OH minus hydroxide, this one is also charged. So this one's going to be more basic than H2O because it has that negative charge. That's one thing to remember. When you're comparing size of molecules to determine their acidity and basicity, make sure you look at the molecules, and you're only comparing molecules sizes when they're in the same group on the periodic table. Electronegativity, only compare when the molecules are in the same row. Hybridization, I just wanted to remind you guys that the greater the S character of a molecule, the more stable the conjugate base. So going back to what I said before, an alkyne is sp hybridized. So it has a greater S character than a carbon that might be sp3 hybridized, which means it would be a more stable conjugate base. And a more stable conjugate base actually means that the acid is, or the conjugate acid of that conjugate base is more acidic. So that's what I wanted to point out down here, where I said look at conjugate base stability to evaluate a molecule's acidity. I always just like to look at a molecule, convert it to its conjugate base, evaluate its conjugate base stability using these rules, SERI, and then obviously looking at charge and hybridization as well. And then the more stable the conjugate base is, depending on whatever we've evaluated using these rules, the more stable a conjugate base is, the more acidic the molecule is going to be. And the more stable a conjugate base is, the less basic it is, because bases love to be reactive. They love to be unstable. So if you're introducing some sort of stability into a conjugate base, either through resonance, maybe through electronegativity or some kind of criteria, if you're including more, or if you're incorporating more stability into that conjugate base, it's going to be less basic, but more acidic. So that's another thing. And then some useful reactions for synthesis that you should memorize, other than the fact that you should memorize every reaction we've learned this semester. But if you're stuck with a synthesis and you don't know what to do, maybe just go through these 3 groups of reactions. The dehydrohalogenation, which we do with alkynes to elongate a carbon chain. That's a great way to elongate a carbon chain. Just remember all reductions. An example is the alkyne to alkene reductions, where we can go from an alkyne to an E or a Z alkene, depending on the reagents you use. Oxidations, including the ones we covered earlier, that convert alcohols to carbonyl compounds, and other types of oxidations as well. Those are all great things to remember, and they kind of show up a lot in synthesis. So if you're ever stuck, just try and go through these in your mind. Another thing is, don't forget to include solvents when you're writing your reactions or reagents in any part of the exam. So for SN2, make sure you include DMSO or acetone along with the SN2 nucleophile you use. So don't just write KCN, make sure you write KCN and DMSO to get full credit. Don't forget workup steps as well. With epoxide opening under nucleophilic conditions or basic conditions, you have to include a workup step so you can reprotonate that OH minus or that O minus. So you end up with like an O minus, and you need to include a workup step so that you can convert that to an OH. And that's basically what a workup does in almost every reaction you'll see. Just don't forget to include them. When you're reviewing your reactions, make sure you especially point out that, oh, this reaction includes a workup step, this one doesn't. So that's another thing. Inert solvents, I just wrote this because I would highly recommend everyone include inert solvents, even though technically they are inert, they're not really doing much. It's always better to include them in case you'll get points off for them. So better be safe than sorry, just include the inert solvents and try to remember them. And CH2Cl2 is one such example. And my final thing is use retrosynthesis as a tool to solve synthesis problems. At least drawing out the last two structures leading up to the product can help you visualize the entire series of steps, or it can help you get some points at least. If you're not sure how to start from the beginning, you can at least start from the end. Personally, I always start from the beginning, and I only use retrosynthesis as a tool when I'm stuck and I don't know how to get from the starting product to even an intermediate product. But a lot of people also use retrosynthesis to solve their entire synthesis. So it's really up to you, but this is my personal way of doing things. I use retrosynthesis as kind of like a last resort. So one way to do it in this example, if you saw the synthesis and you didn't really realize how this would be made, you can look at the ketone, you can look at this functional group, this carbonyl, and you can think of all the ways that we know how to make a ketone. So I just listed some over here. Then when you list all of them, you can eliminate some. So we're probably not going to use alkyne reactions, acid catalyzed hydration, because we're not adding any carbon compound. There's no need to include an alkyne in this in any way, shape, or form. So I'm going to eliminate that. Ozonolysis might happen, but probably not, because if you notice, we have our main carbon structure, we have this tert-butyl group, and then we have this benzene, which both are still here. The only thing that's different is this carbonyl compound added. So there's nothing really cleaving, there's nothing breaking off the original molecules. Probably not going to use ozonolysis. So that's why in this case, I was able to narrow it down to the fact that we were using some kind of oxidation. So I'm just going to pick Jones reagent, but you could also use the oxidations we covered earlier. So knowing that now, we can at least get to another intermediate in this synthesis. So if this was an exam and you were running out of time, or you just simply didn't know how to solve this problem, at least you would get 1 or 2 points for including that last step in this last intermediate. So I definitely think, or oops, I forgot that this molecule with the OH is undergoing oxidation to form this. So yeah, we can draw this intermediate and then get some points here or there. So that is my tips and tricks for you guys to remember for your final exam. I hope you guys found this very helpful, and I hope you guys have a great rest of your semester. I hope you guys ended off well, and good luck on your exam. I know you guys are all going to do great, and just remember all these little details and just take your time. I know it's a stressful situation, but if you find yourself getting stressed out, take a minute, take a deep breath, and just move on, and you will be fine. All right, bye.